Well, I created a little video here on the idea of a drag force and terminal velocity and how those are related to each other. You also maybe categorize this as air resistance. That's another way to describe the drag force. I just want you to know, though, that different textbooks have different treatments of this. So in my class this year, we're using Dr. Knight's book, the engineering level book, and it describes a drag force that's proportional to the square of a velocity. Whereas on the AP test, you generally see a drag force that's proportional to just the velocity, so it's not squared. So I will speak in generalities here, and then for the specifics, you'll just kind of have to apply it to whatever the situation is, depending on who wrote it. So I think most people sort of know what air resistance or drag force is, but I'm going to demonstrate it in pictures here. So imagine we drop a ball, and we're going to draw the forces acting on the ball once it's let go. So we'll imagine that maybe the ground is down here somewhere. We can be really high up, and at the moment that it's dropped, it has an initial velocity of 0. Now, if we were going to throw it, this would be a little different, but we're going to say the initial velocity, v naught, is 0. So there's no motion yet at the moment that we let go. And so if we draw the forces that are acting on it, we just have this one here, Fg, and that's what we consider a free fall situation. And so at this moment, we would have an acceleration of 9.8 meters per second squared downward towards the center of the Earth. But of course, that means it's going to start moving downward. So what is it going to look like in just a moment? Well, it's going to be down here, and it's moving a little bit. So now we still have the exact same gravitational force, call it the weight, but we also have a little bit of upward drag force. So I'll call that F sub d. A little hard to see that label there. But notice that the drag force is smaller than the gravity force, and so there's still a net downward force. And so it's going to continue to accelerate. So I'll show with these little motion tails here the exact same gravitational force, but now we're building up. I don't know if you can see that this drag force vector is a little bit bigger because we have more air molecules colliding with the ball as it falls. And so it continues to speed up. We still have a net force downward, so it's still going to be getting faster. And now I'll show you this critical moment here where it got moving so fast that that drag force exactly balances out the gravitational force. And I'll show my little motion tails here. And now this is where we have reached a point where there is no net force. There's no unbalanced force anymore. And so there will be no acceleration. We have reached what is called terminal velocity. Doesn't mean it's not moving. It means it's not accelerating anymore. And unless something else changes it, it'll just continue to fall at that speed for the rest of the trip until it hits the ground. Now, this is going to depend, that terminal velocity will depend on how big the object is, how aerodynamic or what shape it is, the fluid that it's going through. There's a lot of factors that come into play here. So I think this is probably enough to describe the generalities, and then I'll let the textbook you're using or whatever resource you're using kind of fill in some of the specifics. So that'll do it for now.